Okay, alrighty. Okay, we're back in business. Now, we've been using this equation FR cosine theta. So we already changed it up a little bit on you because we got rid of the x because there's no x that shows up on the AP formula sheet. So I always like to do things with the same symbols they use on the AP formula sheet. Now, you're not going to find the formula W equals FR cosine theta on the AP formula sheet either. So we need to get our formula for work towards, into what it is that shows up on the AP formula sheet and see why it shows up that way. Now, we're going to make our first change to our formula for work. All right, now, work happens to be, multiply force by distance and you get out work. Force, work we said was a scalar. Force though is what?
Vector.
A vector. And position or distance, displacement I guess we should say because it's really a delta, right? Displacement is also a
Vector.
A vector. So really what we're doing is multiplying two vectors together. But when we multiply these two vectors together, we get out a scalar. Now, in the world of vector math, you can take vectors, multiply them together and get scalars. And you can take vectors, multiply them together and get
More
vectors. Those are two different mathematical operations when it comes to vector math. Do you guys ever get into vector math here at all in school?
Did you guys do it in BC lesson?
I don't think they do it in BC. Like, do you have a math class beyond calc at all?
No.
Okay. Well, there is this world of vector math out there that says if you're going to take two vectors and get out a scalar, what you're doing is called the vector dot product. Alrighty? So if you go on to higher levels of math, and if you go on to, a technical, engineering or physics or something in college, you're going to see this notation. It's called the vector dot product. It's a mathematical way of taking two vectors, multiplying them together, and getting out a scalar. So it takes two vectors and produces a scalar. Now, we treat our vectors very, and when it comes to AP Physics, we just deal with this force at that angle. That's not the only way to write a vector. I can write, so this is just like a little side note now. So you can write the force is 500 newtons at 20 degrees to the horizontal. That's one way of writing that force. In the world of vectors, there's a whole nother way of writing forces, or any vector, and it's called IJK format. Have you ever heard of that?
Yeah.
Okay. I could have written this vector, this force, as 500 cosine 20I plus 500 sine 20j. And that's another way of writing the vector. They don't use that notation on the AP exam. But if you go into, I went into engineering and I definitely used this in college. As soon as I got to my first statics class, everything was in IJK format all of a sudden. So at least you know what it's referring to. Basically, I is a little unit vector in the x or horizontal direction. J is a little unit vector in the y direction, and k would be a unit vector in the z. So if you had a three-dimensional vector, again, something they don't do on the AP exam, you would have a z component as well. Now, if you get into vector math, there is there's stuff you have to do when you have your vectors in IJK format in order to get the dot product out. There's a mathematical approach that you have to take, and so on. Because they'll say I dot I is this, J dot J, it's all this stuff that you'll learn if you go on, but you don't need to worry about it here. But just know that that's what the dot product is. And you're going to see when you get to torque, You haven't done rotation yet, right?
We did, rotation?
No. Uniform circular motion, but not torque.
Okay, so when you get to torque, you're going to find out that that's the vector cross product between R and F, and again, that's going to give you a vector out, and then IJK format, that's a whole nother procedure you would have to do with the vectors. Again, none of that's on the AP exam. But we need to bring it up because this is how they write this on the formula sheet. So our very first change that we're going to make to our formula, we know that it's FR cosine theta. The very first change that we're going to make to it is we're going to rewrite it as a dot product. So we're going to just say work equals F dot R. And that dot doesn't mean multiply together. That dot means do whatever it is the vector math tells you to do to multiply those two vectors together to get a scalar. But we'll leave that all for whatever math class you take in the future. So the first thing you're going to see on the exam, if you look at the AP formula sheet, is they're going to have this dot in there. Okay? And if we had vectors in IJK format, then we would have to do the whole, calculation that you have to do with I dot j, and so on and so forth. But we don't have to do that here. But that's the way you're going to see it on the exam. When we see the dot product, all we're going to do is do what? Change it right back to FR cosine theta. Because if we're not dealing in IJK format, F dot R is FR cosine theta. So that's all you need to know is F dot R is going to be the same algebraically as FR cosine theta. But the dot product is, does have significance. It's not just that they're telling you it's a multiplication sign, because you can use dot to say you're multiplying things together as well. This dot is a very specific dot product. And you're going to see that on the AP formula sheet. But again, if we look at it this way, this still assumes what?
That it's a constant force.
Still assumes it's a constant force. So that would still have to be a constant force, and we don't want to deal with this constant force anymore. So we need to come up with a way to deal with any kind of force. And then eventually we're going to write down the equation that they actually have on the AP sheet. All right, so we started off with work equals FR cosine theta, and now we've changed it to work equals F dot R. All right, but now we got to get out of this constant force, because on the AP exam, yeah, do you see constant forces more often than not? Yes. However, are they going to throw variable forces at you?
Yes.
For sure, so we need to be able to deal with a variable force. All right, so we have to go down that road now and rewrite this equation once again so that we can deal with variable. Is that green okay?
No.
All right, green is out. We'll just put the green over there. We'll put this green over there. We'll go with red. I like to change up my colors. That's good?
Yes. So this is the point where this is new.
Yeah.
All right, so variable forces is where we are headed. All right, so if I wanted to see how force was varying, since I'm talking about moving this thing through a distance, it would be great to know how force varies with distance, right? Because that's what I'm trying to do. I'm trying to move it through a distance. So it would be nice to know if my force at 0 meters is a little different than my force at 1 meter, my force at 2 meters, and so on. The best way to ever show how force is related to position would be to draw what?
A graph?
A graph is a great way of showing how force varies with, and we're not going to write x because we're dealing with the new AP land of R. All right. If we have a constant force, what's this graph going to look like?
Straight line.
It's going to just be a straight line, right? Let's try brown. So that would be a constant force. And let's say we moved the object to R1. Could I use work equals FR cosine theta here?
Absolutely.
I could, and I would end up multiplying the F by the R and getting a cosine of 0, and I would get F times R. What's the area of this curve? If I calculated the area of that curve,
Base times height.
let's call this F1 or whatever. If
F1's
I,
R1.
what's that?
F1.
The area of this curve is F1, R1. If I calculated the work by doing FR cosine theta, what would I get? F1, R1, we'll say that that's, just at 90 degrees, at 0 degrees, so it's F1, R1. What do we got here?
Same thing.
It's the same thing. So the very first thing that's going to help us out here is work is equal to the area under an F versus R graph. Where R again stands for what? Position. So I don't care whether they write it F versus X, F versus D. Again, this is just position. All right. Well, that was super easy to calculate that area, wasn't it?
Yeah.
Because it was just a rectangle. Now we got to make things exciting. Because we can't keep everything constant. Because sadly, our life isn't constant. Things are always changing. So forces included. So what if we had an F versus R graph and we had something crazy like that?
You have to count the number of boxes inside the graph.
Okay, so what you're saying is you want to approximate
Sure.
or estimate the area under that graph. Because that's what you really want to do still, because we know the area under this graph is, equal to the work. I'm going to just call this cosine theta so that we know we're only looking at the force that it's actually making this, that's actually doing any work.
Yeah.
All right, so I can easily calculate the area under this curve. So have you gotten to integrals in calculus?
Yeah.
All right, so what we're heading to is, well, gee, whenever we're faced with a situation where I have this strange shape, the best thing to do is approximate it. And I'm going to divide it up into a whole bunch of little rectangles. And those rectangles are going to all have different heights. And they're all going to be delta R y. If I wanted to find then the total area under that curve, because remember work equals area, I would just have to add up all the F cosine theta delta R's, right? Because F cosine theta would be the height of this thing, and the width would be delta R. That's going to get me an approximate solution.
Will we ever have to do something like that on the AP test? An approximation like this?
I've seen it on multiple choice questions. I've seen it with impulse. I haven't seen it with work, but I would say, yeah, I would say you could be in a situation where they don't give you the function, but they give you enough to approximate an answer.
Okay.
And so on. That gives us an approximate answer. How big does delta R have to be to get me the exact answer?
Point negative infinity? I don't know.
So to improve accuracy,
I don't know.
Infinitesimally small.
delta R has to approach 0, doesn't it? It has to get so small that it's just slightly bigger than 0 itself. When it comes to math, when we talk about these infinitely small changes in R, we don't call them delta R's anymore. What do we call them? dR's. So delta R is going to approach 0. It becomes what we call a dr. And a dr is just a mathematical way of saying an infinitely small change in R. So it's teeny tiny. So what we're going to to do now is we're not going to sum up the f cosine theta delta r's. We're going to sum up the f cosine theta dr's. But now in math, we use a totally different symbol for summing up infinitely small things. What do we use to sum up infinitely small things? An integral. So this is going to become the integral of f cosine theta dr, because we need to sum up infinitely small things, so it's just a different type of summation sign, which we call an integral, which has its whole world of, formulas and things associated with it. But now we've already said f cosine theta r can be replaced by what? Back when we had our dot product on the board, f cosine theta r was just f dot r, correct?
Oh, yeah.
Guess what f cosine theta dr is? F dot
dr.
dr. And the equation that you see on the AP sheet is that. That's what you see on the AP formula sheet. Just the integral of f dot dr. This is the generic equation for work. This is the equation you can always use 100% of the time, because it's always going to work, because it doesn't assume anymore that f is constant. So that's what I call it, one of my generic equations. So when I teach physics, I'm always talking about generic equations and specific equations. Work equals Fr cosine theta is a very specific equation, because force has to be constant, but this works in any situation at all. And this is what you see on the AP sheet. So how do you deal with this equation? Again, more often than not, if you had a problem and you started with f dot dr, well, the very first thing you do is get rid of the dot product, because we don't do the dot product in AP Physics because we don't have IJK format. So what do we replace it with? We just get rid of it and put in the cosine theta dr. And then if your force was constant, what does that mean when it comes to integration? If we have constants in our integral, what do we do with them?
Just take them out.
Take them out. So if our force is constant, we're assuming the angle that it's at is constant as well, or else it wouldn't be, a constant thing. We can pull that out. What's the integral of just dr? And what does this become? Fr cosine theta, the equation that we've used all along.
Yeah.
So this equation, the generic equation, becomes the equation you've been using, the specific equation, just by, doing the mathematics out, saying the force is constant, pull it out, theta is constant, pull it out, take the integral, oh, and there it is. This is the old equation for constant forces. But we want to be able to use this one. And that's what we're going to spend a little time on right now. We're going to try some problems where we have forces that aren't constant, and we want to calculate the work. All right, so we have our new equation. All right, here's some problems. So let's erase. Any questions so far? So it's just a new way of looking at the formula. And this equation is now going to let you have variable forces, because we know what to do with them now, because we just need to take an integral of them with respect to position.
In what format are we going to be seeing these variable forces? Like
More often than not, they'll show up as springs,
springs.
because springs are just a very natural variable force that varies with position. Because when you're using work, you want a force that's varying with position, because it's the integral of f dot dr. If I came in and gave you forces 3t squared minus 7t, and I gave you it varying with time, work's not going to be the approach you want to take. Because if I plug in, 7t squared minus 3t dr, can I do that integral?
No.
Because the variable's not matching the dr. Now, can you work to change the variables to get them to match the dr? There's things you can do from a mathematical standpoint, but sometimes they're just a nightmare. Okay, and you'll see that, you know, as you go throughout. Like my kids saw it a lot when we did center of mass and rotational inertia, that there's ways to, you know, rewrite variables so that things match up. But if you got a force varying with time, work's not going to be the approach you probably want to take. You're going to probably want to take some other approach that deals with forces varying with time, and you're going to learn probably in your next unit that that would be a momentum and impulse approach, because that deals with forces varying with time.
Okay.
Okay? Forces varying with things like velocity. That's drag force. Did you guys do that already? So that you ended up having to write a differential equation for those forces. Forces that vary with position to the first power, you're going to find out when you deal with simple harmonic motion. You can also do differential equations with those. So with like a linear spring, you can take a work energy approach, or you could take a simple harmonic motion approach. But once you get x varying to anything other than the first power, you're stuck with like work and energy. So that makes sense.
Yeah.
So